We turn our attention now to the derivative. I know the last section was a monster, and you're probably still exhausted. So the good news is this section is more straightforward, and the video will be much shorter. When we're looking at the derivative, remember it is one of the three major concepts or constructs in calculus. The limit, which is the foundation of everything, the derivative, and the integral. When we think about the derivative, we think about the slope of the tangent line. In physics, this gives us the instantaneous velocity. It will also give us the rate of change of one variable to another. Let me share my screen with you and we'll get started. Here are the learning objectives we're going to cover in this section. Recognize the meaning of the tangent to a curve at a point. It's the derivative. Calculate the slope of a tangent line. It's the derivative. Identify the derivative as the limit of a difference quotient. That's the formal definition of the derivative. Calculate the derivative at one value for a function. Say x equal 2. I want to know what's the slope of the tangent line to the curve of the function at x equal 2. We'll describe velocity as a rate of change, and we'll again talk about the difference between average velocity and instantaneous velocity. We'll also estimate the value of the derivative from a table of values. Now, in order to find the derivative, we will eventually come up with derivative rules or derivative laws, much like we did limit laws. This will allow us to find the derivative more quickly without having to go back to the limit definition. In this section, however, we stay with the limit definition to get a firm foundation of what the derivative truly is. To do that, let's take a look now at tangent lines and secant lines. Recall that the secant line cuts through the graph. So if I have a curve and it looks something like this, and I want to evaluate the secant line, I'm going to take a point here and a point here, and I'm going to put the line that cuts through the graph connecting those 2 points. This represents average velocity if you have a position time graph. It's also given the slope by the difference quotient. The difference quotient, you may remember from pre-calculus or college algebra, is given by this representation that you see right here. It's basically y2 minus y1 divided by x2 minus x1. This is f of x minus f of a over x minus a. In the case of the particular one I'm looking at, I might say this one's a and this one's x, or I could reverse it. Again, it won't matter for the slope. It'll come out to the same value. Now, this is the slope of the secant line. But what about the slope of the tangent line? When I think about the slope of the tangent line, let's say I'm at a different point, then I'm talking about the line that barely touches the curve near that particular value. Let me call this value here b. I'm looking at the slope of the tangent line when x equals b. This corresponds to instantaneous velocity, and that slope represents the derivative. Let's take a look at another image that's larger so I can write a little bit more on it. When we're looking at this, you'll again see that we have a secant line through AF of A and XF of X. The line connecting these two has a slope given by the difference quotient. Now, what if I were to take a point and I were interested in the slope of the tangent line right here at A? If I wanted to know the slope of that blue line, I could fix A so it didn't move, and I could take closer values to A than my original X. Now, as I do this over and over again, So let me take another one. You'll see that the slope of the secant line is approaching slowly the slope of the tangent line. In other words, the limit of the slopes of the secant lines becomes the slope of the tangent line. In that sense, then, it makes sense that the derivative would be the limit as x got close to a of the difference quotient. And that is, in fact, the definition. The derivative is the limit of the difference quotient. Let me write it out in notation. As x gets close to a of f of x minus f of a divided by x minus a. It's a limiting value, which means x never actually gets to a. So we don't have to worry about division by 0. As the width of the interval goes towards 0, then the slope of the secant line approximates the slope of the tangent line. You can explore this relationship with the two applets below. Let me open them for you now. Right. This is the first applet created by Dr. Jack Jackson II. In this particular one, he wants to take a look at the difference quotient. And he wants to also look at the derivative, which is that slope of the tangent line. So what we're going to do is we're going to come up here and choose a function. You're allowed to change the function if you want. And we're going to choose the value at which we want to know what the derivative is, a. We're going to set an h value. We'll see what that leads to later on. Let's look at the difference quotient. Now, you'll see that in this particular case, he has written a difference quotient a little bit differently than we wrote it. We had f of x minus f of a over x minus a. Instead, what he's done is he said, well, x is a plus scoot over a little bit. Basically, h is just a hair off of the a. So the x becomes a plus h. And then when you subtract a plus h minus a, you get h. So the h is the value of x minus a. It's how far x is from a. This represents exactly the same thing. It's another way of writing it. This gives us the slope of the secant line because it is the difference quotient. It's sometimes written delta y divided by delta x, the change in y with respect to the change in x. Over here on the graph, you can see that the h value, which was set over here to be 0.5, is 0.5y. Now you can look at the change here in the y values between these 2 points. The slope of the secant line is given by the ratio of the change in the y divided by the change in the x, which he's computed for you here as 3.3. Now the question is, what happens if we move that x value closer to our a value? Now I've got to find a, which looks like it's right here in teal. So I'm going to leave a there, and I'm going to grab hold of this point. Oops, the wrong one is moving. Where was it? Okay, close enough. I'm going to move a plus h. Oh, that's not letting me do it either. How can I do it? Let's see. Let's move the h value. Ah, that did it. I'm getting the point closer and closer. As I'm doing that, you can see the slope of the secant line that's connecting the two and how it's getting closer to the value of the tangent line. When we look at the derivative, that's the line in red. Let me put up a different function that may make it a little bit more clear. Let's put up the following. I'm going to try x minus 2 times x minus 3 times x plus 4 times x. Okay, hit return. All right, now I can see that I've got a curve here, which is kind of, well, wiggling, if you will. If I look at the curve, and let's say I want to fix my A value, and I want A to be the number, how about 2? Let's see if I can click in the box. A is now 2. What I want to do is I want to scroll in on the graph a little bit. And I want to look at the secant value for values that are pretty far away. So I'm going to increase my H quite a bit. All right. If I look right here, you can see in purple the slope of the secant line connecting A f of A with f of A plus H. Now, what we have is the difference quotient. What I want to do now, you can see in red that this is the actual tangent line at 2. I'm going to move this value by decreasing H. Watch what happens to the purple line, which represents the secant line, as I decrease my H values. Went to 0, then it got steep, then, oh, do you see that the purple is getting so close to the value of the red tangent line? The closer I get, the closer the slope of the secant line matches the slope of the tangent line. This is a nice little applet, and it gives you the opportunity to also see worked out on this side the actual definition of the derivative, which you can see here is the limit as h goes to 0 of f of a plus h minus f of a divided by h. And he's giving you the true value of negative 12 for the derivative, slope of the tangent line. And we can see that the slope of the secant line is getting closer and closer as our value x moves closer and closer to a equal 2. Now let's take a look at the other applet. The second applet, I believe, was created by Tuyatdong Van Yamada. And you also have the opportunity to change the function that you see here. You can also set the value of a by entering it into the box. When you look over here, you see that she's calculated the difference quotient, which is slope of the secant line. If we're looking at this point and a is negative 3, this blue line is the secant line. I can also click in the box for tangent line, and I can get the slope of the tangent line. Now the tangent line is up here in black. Watch what happens as I decrease the value of h. Watch what happens to the actual value of the slope of the secant line. It should be getting closer and closer to 4. It's increasing 2.5, hitting 3 now. It's getting really close. I think I've run out. It's practically 4. We'll learn later this semester, in just a couple days, how I knew it would be 4 based on the equation of the tangent line. You may have already guessed it's the coefficient of the x. And we'll talk today a little bit about why that's so. Let's work an example now, just to make sure that we all remember how to compute the slope of the secant line. On this particular one, I want you to go ahead and work both example 1 and example 2 to find the slope of the secant line, connecting the ordered pairs x1 and f of x1, x2, and f of x2. Then turn the video back on and we'll compare our results. Did you get 8 for example 1? First, we find the function value at -1, which turns out to be -11, giving us the ordered pair -1, -11. Then we find the function value at 3, giving us the ordered pair 3, 21. Then we apply the difference quotient. It doesn't matter which point you take first, as long as you're consistent. The 21 and the 3 have to come from the same ordered pair, as do the -11 and the -1. And that gave me a slope of 8. Now, it's not surprising that I got 8 because my function, 8x minus 3, is a line. And the tangent line to a line is the line itself. And again, notice the coefficient of our x term is 8, which indicates that's the slope. Now let's look at example 2. Example 2 involves some cube root functions. Remember that the 2/3 power means the cube root of the number squared. And the 1/3 power means the cube root. When we substitute 1, we end up with a value of 8 for an ordered pair of 1, 8. When we substitute the value 27, we have to be a little more careful, taking the cube root of 27 to get 3 first, then squaring the 3 to get 9, then multiplying by 6 to get 54. We end up in this case with the ordered pair 27, 60. Then we compute the slope of the secant line, which turns out to be 2. You'll see right here in the graph, which is kind of interesting, and notice it's got this sharp point here near the origin. And I've drawn the line connecting the 2 ordered pairs, showing it is the slope of the secant line. As we're going to see, because this is a sharp pointed part, we will not actually have a derivative there, even when the function is defined there. Sharp pointing parts do not produce derivatives. As x gets closer and closer to a, the slope of that secant line gets closer and closer to the slope of the tangent line. Instead of using x as Dr. Jackson did in his particular applet, you can write a plus h as well. A plus h is the same thing as x. It just means a plus a little bit over to the right or the left. It doesn't matter. Then you're going to have the difference quotient. This becomes the slope of the secant line, which we can rewrite as f of a plus h minus f of a over, well, this should be the difference in the x values, which is a plus h minus a, which reduces to h. This is probably the one that we use the most often in mathematics when we're finding the derivative. Now, when we look at the graph up here, you can see that they've relabeled x and a as a and a plus h. It's the same point and the same concept. Again, as x gets closer to a, the slopes of the secant lines get closer to the slope of the tangent line here in teal. The tangent line has a slope that is a limiting value. This is the derivative. But derivatives don't always exist, as I said earlier, in that function that had cube roots. So what does make the derivative exist and what causes it not to exist? Let's figure that out by taking a look at the graph of square root of x. In the first graph right here, we can see that we have the function x plus 1 over 2, And we also have the function, the square root of x. And we're trying to figure out whether or not the derivative exists. When we're looking at this x plus 1 divided by 2 is the tangent line at the point x equals 1. We want to zoom in on this part of the graph and look closer near 1 to see what's happening. The first graph goes from x equals 0 to x equals 4, but the second graph zooms in on just this grayed out portion, and it comes in from 0 to 2. Again, we're looking, I believe, here at x equals 1. What do you notice about the relationship between the curve and the tangent line? Well, they're very close, at least near to 1. They're very close. The further from 1 it gets, however, they split apart and become very different. Now let's look at the bottom two graphs. In the bottom two graphs, they've again taken this graph that we had in the upper right, and they're going to zoom in on just this portion right here. So now they're going to go within 0.1 of 1 on either side. So I think that's right. 0.1 of 1, well, a little more than 0.1 on the left. So when we're looking at the graph, now what do you notice as we zoom in on it about the relationship between the tangent line and the graph? Well, they're getting nearly indistinguishable. When the derivative exists, then if you zoom in on that particular point enough, the curve of the function becomes nearly linear, the slope of the tangent line. That's what causes the derivative to exist. That as you zoom in, the curve itself becomes nearly linear near that point. Now let's take a look at the graph, the absolute value of x, specifically at the point 0, 0. If we're looking at this point, it has a sharp corner. If I zoom in, my first window is from 2 to 2. My next window is from negative 0.5 to 0.5. Notice it's still a sharp corner. A corner is not a line. It's a point, a pointy part, as I like to put it. Then I zoomed in again between negative 0.1 and 0.1, and again between negative 1 1,000 to 1 1,000. It doesn't matter. No matter how close I go in on the graph of the absolute value of x at the origin, it will never become a single tangent line. Now, why is this causing a problem? What's the issue here? Well, we're going to come back to the definition of the slope of the tangent line, which is the derivative. The derivative is the limit as x approaches a of f of x minus f of a divided by x minus a. It's the limiting value of the slope of the secant line. When we look at the curve up here, what do you notice coming from the right? Well, it looks like the slope from the right is 1, but the slope from the left, it looks like it's negative 1. The two sides do not agree. And because they do not agree, the limit does not exist at 0 for the limit of the difference quotient. The limit of the function exists, but the limit of the difference quotient, the derivative, does not. Let's look at a couple of different ways of writing the definition of the derivative. There are actually 3 that we'll learn. The first one is most useful for finding the derivative at a particular point. I know I want the derivative at x equals 2. So a is the value 2. Then we'll use the limit as x approaches a of f of x minus f of a over x minus a. What if instead we want a general formula that will give us the derivative anywhere on the function. I don't know what particular a value I want. In that case, we often define the slope of the tangent line, the derivative, as the limit as h goes to 0 of f of a plus h minus f of a over h. We can replace the a with an x to get a more general formula. You can use this formula if you know what the value of a is. In that case, then you will replace that value with the number that represents a. This is another way of writing the same one. This is probably the one that we use by far the most often in mathematics to formally find the derivative of a function. There is a third definition that we have as well, and this is one that gets used more often in physics. So if you take a physics class, instead of seeing h, you'll see delta x. Delta x just represents a small change in x, which is what h is. Again, what we're looking at here is some kind of curve, some value of a, or in this case, x, and then we've scooted over just a little bit. And that change there is delta x or h. And so we have the point x and the point x plus delta x. In other words, delta x is just being substituted for h. I do expect my students to commit all three versions to memory. I will not allow you to write this down on an index card. And I expect you to be able to apply any of them to find the slope at a particular point A, or to find a formula for the derivative at any point A. Again, we typically use this version with a in it, the limit as x approaches a of f of x minus f of a over x minus a, when we know exactly where we want to find the derivative. Let's go ahead and look at example number 3. We'll work example 3 together, and then some of the later ones I'll let you try on your own. In this case, we need to know what f of x is, but it's given to us as the square root of x. We're asked to find the derivative when x is 4, which means that a is 4. If a is 4, I also need to know the value of f of a, which would be the square root of 4, the principal root, which is 2. This, of course, represents the ordered pair of 4, 2. That definitely is going to be on the graph. And I'm trying to find the slope of the tangent line at that point. So I take the limit as x approaches 4 of the square root of x minus f of a, which was 2, divided by x minus 2. Now, there are two techniques on this one that can be used to find the limit. We're going back to the limit definition of the derivative, so you'll have to use the limit laws that you learned in chapter 2. There are two ways. I'll do the longer method first, and then I'll show you the shortcut. The longer method says, okay, I have this, I've got a conjugate, I've got a square root of x, so I'm going to multiply by the conjugate of the one with the radical, divided by itself, so it becomes the number 1. This then gives me the limit as x approaches 4 of x minus 4, did I do that right? Divided by x minus 2 times, I've got some error. Duh. The a value is 4, so it should be x minus 4. I was wondering where that went. And this will become the square root of x plus 2. I guess writing the value of f of 4 has messed me up. I keep wanting to use it. Now notice that we have a common factor of x minus 4. which is then going to allow us to write that the limit as x approaches 4 of 1 divided by the square root of x plus 2, and then we can substitute in. If I try to substitute in at the beginning, I get the square root of 4, which is 2, minus 2, which gives me a 0. And in the denominator, I get 4 minus 4, which is also 0. It's that indeterminate form. We're not actually getting to 0 over 0, so we don't have to worry about the fact it's not defined. We're limiting. We're going close. So then I multiplied by the conjugate and reduced it. Now I try to substitute the value again. When I substitute the value this time, I get a number. In fact, I get the number 1/4. Now I said that there's a shorter way to do this one. So we'll go back to the original representation. This is the limit as x approaches 4 of the square root of x minus 2 divided by x minus 4. Notice that the square root of x is the square root of the first term in the denominator, and 2 is the square root of the 4 in the denominator. That means that I can factor x minus 4 as the difference of 2 squares. Now, again, I would first substitute 4 in, leading to the indeterminate 0 divided by 0, and then I would try factoring. This would give me the square root of x minus 2 on top, and the conjugate pattern, square root of x minus 2, square root of x plus 2 in the denominator. Then these cancel, and I've come directly to this step right here. And from there, the result is the same. This gives me a slope of 1/4. Now, how can I actually write the equation of the tangent line? Well, it's not difficult to write the equation of the tangent line if you remember your point slope form of a line. When you have point slope form, you know the value of y1 and you know the value of x1. You also know the slope. I do know the slope. I just got it to be 1/4. Now I need a point, any point on the line. Well, let's use a f of a, which is 4/2. The y value is 2. The slope is 1/4. And the x value was 4. This equation that you see here will give you the equation of the tangent line. I've gone ahead and graphed it for you to show you the relationship between the two. So let me open it up now and turn those graphs on. And you can see that in the graph of our function, square root of x, that at 4/2, I have computed, in fact, the tangent line. Let's now take a look at our next section. In the next section, we want to take a look at the derivative of a function at a specified point, which is what we just did. Now we have 3 definitions for the derivative: the x minus a version, the a plus h version, and the a plus delta x, or x plus h and x plus delta x. If I know what a is, I know it's 4. I can replace the a in each of these formulas with 4, and then I can compute the slope of the tangent line using any of the 4 different versions. You should be able to do this on an exam. Let's take a look at example 4, which asks us to use the middle form with a plus h to find the slope of the line to the graph x squared plus 3x plus 2 at x equal 1. In order to do that, I need to write down what my values are. A is equal to 1. Then I have f of a, which equals f of 1, which becomes 1 squared plus 3 times 1 plus 2, which would give me 6. This represents the ordered pair 1, 6, which is on my graph. To complete the difference quotient, the easiest thing to do, honestly, is to do each part one at a time, then substitute those values into the difference quotient. Otherwise, you end up with a lot of needless writing and rewriting, which can be kind of, well, obnoxious. All right, so let's go ahead and write this one down. The next part we need is f of a plus h, but I know that a is the number 1, so I want 1 plus h. This is more complicated. This means 1 plus h squared plus 3 times 1 plus h plus 2. You're going to have to multiply it all out. This is going to give me 1 squared plus 2h, double the outside and inside, plus h squared plus 3 plus 3h plus 2. Now, what do I have in the numerator? In the numerator, I have f of a plus h minus f of a. I can combine my 1 and my 2 and my 3, my 2h and my 3h. When I do that, it will give me a simplified version, which I can then use in the equation. So this will give me h squared plus 5h plus 6, I believe. Now let's put it together into our formula, the limit as h goes to 0 of the difference quotient. H squared plus 5h plus 6 minus the 6 that came from f of a. All of this is divided by h. The 6 minus 6 cancels, and this gives us the limit as h approaches 0 of h squared plus 5h divided by h. We have addition in the numerator, so we're not allowed to cancel until we only have one term in the numerator, which means we have to factor. We take out the greatest common factor of h, and this gives us the limit as h approaches 0 of h times h plus 5, all divided by h. Notice we can now see that factor of h that was giving us the 0 over 0, and this will now cancel, leaving us with the expression, the limit as h approaches 0 of h plus 5. Now we substitute, and we get 5. The slope of the tangent line is 5. To write the equation of the slope of the tangent line, we take our point, 1, 6, and we write y minus 6 equals 5 times the quantity x minus 1. Let's take a look at our graph and see if that matches with our expectation. You can see here that it does in fact match, that we've got the tangent line at the point 1, 6. Let's now turn our attention to example number 5. Example 5 is a little bit more complicated because it has a complex fraction in it. Remember, for a complex fraction, you want to find all the little denominators, multiply by 1 in the form of that divided by itself to get rid of the complex part. Pause the video, work it out, then turn the video back on, and we'll compare our results. So let's see how you did. On this particular one, we're told the function is 7 divided by x, and a equals 3. Next, we need to compute f of a, which is 7 divided by 3. Then we write the difference quotient inside the limit as x approaches the a value, which is 3. This gives us 7 over x minus 7/3, all divided by x minus 3. When we try to substitute the value of 3, we get 0 in the numerator and 0 in the denominator, which is indeterminate. So we know we have to do some algebra. It's easiest to get rid of the complex fractions. So we look at this difference quotient. We find all the, oops, sorry, my dog's at my feet, my little denominators. I can think of this x minus 3 as x minus 3 divided by 1. That means my little denominators are the x, the 3, and the 1. The lowest common multiple of all three is 3x. So I then multiply the difference quotient by 1 in the form of 3x divided by itself. But I wrote it in complex form to help me keep the parts straight. I distribute the 3x over both the 7 divided by x and the negative 7/3. This leads to 21 minus 7x. Then I multiply the 2 together in the denominator, but notice I didn't multiply that part out because I'm hoping that the x minus 3 will cancel. When I look at 21 minus 7x, I can then factor out a negative 7, which does give me the factor x minus 3 to cancel. I then find a limit as x approaches 3 of negative 7 over 3x by substituting the value of 3 for x, which gives a tangent line slope of negative 7/9. Finally, I write the equation of the tangent line as y minus the y value for f of a equal to the slope times the quantity x minus a. Let's take a look at our graph and see if this one also meets our expectations. I've got to turn all of these off, and now I'll turn the others on. And you can see that indeed we do have a rational function, 7 divided by x. We have our point, 3 7/3, and we found the tangent line at that point. We're now going to turn our attention to the next example in the notes. For the next example, we have x squared plus x, and we want to use the same formula, f of a plus h minus f of a divided by h. In example 7, we want to try it with delta x. But keep in mind, delta x is just another way of writing h. It's no different. I want you to work out both of these on your own, then turn the video back on so we can compare our answers. All right, by now you should be becoming an old hand at finding these limits. In this case, we want to use the delta x definition. Don't think of delta x as two things, delta and x. Think of it as one thing, delta x. Delta x represents one value, h, the change in how far you are away from a. In this case, our a is equal to 6. And when we substitute it, we get the y value of 2. This gives us the ordered pair 6, 2. To find f of a plus delta x, we replace a with 6. This gives us the square root of 4 plus delta x. Again, delta x is one thing, not two things multiplied. Now I put this into the difference quotient in the delta x format. When I write it, notice that if I substituted 0 in place of the delta x, I would get 0 over 0. So I know I have some algebra to do. I've got the square root and another term, so that reminds me of using the conjugate. I multiply by the conjugate divided by itself. I don't multiply out the denominator because I'm hoping a factor will cancel from the denominator. This leads to 4 plus delta x minus 4 in the numerator, which reduces to delta x. Now I can cancel that delta x as a common factor. And it leaves the square root of 4 plus delta x plus another 2 in the denominator. At each step, I can try substituting 0 for delta x, but I get 0 over 0 until I cancel that common factor. Now I can substitute again, 0 in place of delta x, leading to a value of 1/4. The tangent line becomes y minus 2 equal 1/4 times x minus 6. Let's look at this particular graph. There it is. And there it is. This is the one I just did, right? Yes. Okay, just making sure. You can see again that I found the tangent line at the ordered pair 6, 2. We now want to take another look at velocity, and we want to think about the instantaneous velocity and the average velocity. Average velocity, we've already discussed several times, as the slope with a secant line. If s of t is a position function, then s of t minus s of a divided by t minus a will give us the average velocity over the interval from a to t or t to a, depending on which side of t it's on. Now, this, of course, is the slope of the secant line. To get instantaneous velocity, when the change in time is 0, we do the derivative. The derivative is also written using what's called prime notation. This prime notation appears to the right of the function name. In the power position, it's actually a cursive or italicized apostrophe. It is slanted slightly. We read this s prime of a, meaning the derivative at a, the slope of the tangent line. And it's the limit as t approaches a of the difference quotient. Let's now look at a couple of examples calculating instantaneous velocity. This is going to be exactly the same as what we did before, but now our function is called s of t instead of f of t. You can use any of the three formulas you want to find the instantaneous velocity at t equals 1 second. Pause the video to work it out now. Let's compare what we've done. In this problem, we have a rock and it's dropped from a height of 64 feet. So it's up above the ground. It's released, we let go, and it begins to fall. And as it falls, its position above the ground is given by this equation, negative 16t squared plus 64. It must hit the ground at 2 seconds because that's our interval, 0 to 2. We want to use one of the formulas for finding the slope of the tangent line at a point to find the derivative, its instantaneous velocity 1 second after it is dropped. A must be 1, so we compute s of a, which turns out to be 48. I chose to use the a plus h version. Notice I changed the name from f to s, and then I computed s of a plus h. I had to multiply by the negative 16 after I had done the square. Once I simplified that, I put it back into the formula and tried to substitute 0 for h. H, however, caused this to become 0 over 0. So I took the 48 minus 48 and canceled them. I tried to substitute 0 for h again, and again, I got 0 over 0. So I factored out the common factor of h and canceled it. Notice you could also have taken out a negative 16, But you don't have that in the denominator, so it's not going to cancel. There's no advantage to taking it out, but no disadvantage either. This then left me with a form that did not give me 0 over 0. Instead, I ended up with negative 32, which represents negative 32 feet per second. It's dropping 32 feet each second at the instant, 1 second after it was released. This gives me the equation you see here for the equation of the tangent line. Let's now turn our attention to a more difficult example where we want to use a table to estimate the velocity because we don't yet know how we would compute the difference quotient with an exponential. Our function is 10e to the 0.5x, and we want to find the velocity at a point compared to the point 0, 10. In other words, we really want to know what the instantaneous velocity is at 0, 10, and we're going to use points close by in order to compute it. We want to find the average velocity, slope of the secant line, for each point in the table given below. Then we'll estimate the instantaneous velocity from that and write the equation of the tangent line. Here is the particular table you're to fill out. Go ahead and fill out the table now, then turn the video back on and we'll continue the problem. Let's now look at the table of values. When I look at the table of values, what I'm computing is the slope of the secant line, not the tangent line. So I take the function 10e to the 0.5x, and I replace each x with the numbers in the far left column. Then I subtract 10, the y value at the point I'm interested in, and I divide by the difference in their x coordinates. This gives me about 4.877 for the first one. And I wrote out the second as well, but the pattern is the same. So I finally just wrote the values that you get. As you look at these values, you can see that it is getting closer and closer to 5. So my estimate for the derivative at 0 is 5. Notice that we can write the derivative in prime notation as the derivative of f at 0 equals 5. If the function was called s, this would be s prime of 0 equals 5. And then I wrote the equation of the tangent line. Here is the graph of the function, and the point 0, 10 is right here. Then you can see next to it in the next photo a picture of the original function and the tangent line graphed next to it in purple. It is touching the graph at that one point. Let's now talk about instantaneous rate of change and other ways that we can use the derivative. It doesn't always have to be instantaneous velocity and average velocity. We could talk about the change in profit with respect to the cost of an item. Or we could talk about the rate of change of a flood compared to the amount of rainfall that we got. Just because you get 3 inches of rain doesn't mean you're going to get 3 inches of water on the road. It could be 5 because it drains from other places. Let's take a look now at using the derivative to represent an instantaneous rate of change at a particular value a, called f prime of a. We can use this for all kinds of problems. This is how calculus became so ubiquitous, just everywhere, because it can give us the change in one variable compared to another at a particular point. Let's look at this example. A coffee shop determines that the daily profit on scones is obtained by charging S dollars per scone according to this quadratic equation. The coffee shop currently charges $3.25 per cone. We want to know if we change the price, do we get, or the, yes, the price. If we change the price or profit, P is profit, S is price. If we change the price, what change do we see in the profit? So if we increase this particular value of S, would it increase our profit? If it doesn't, then we may want to change the price of the scone. So in this case, we're hoping that if we increase the price, it increases the profit, that we're still getting a positive profit. We're hoping to get a positive value for the derivative. We're going to find P prime at 3.25 or $3.25. We're going to use the same formulas that we have before. Go ahead and compute the one you want. I'm going to choose the f of x minus f of a as x approaches a for this particular problem. Pause the video now and give it a try. I hope that you chose more wisely than I did, and you did not follow my lead and use the f of s minus f of a over s minus a formula. It was a nightmare. I would have been better off with the a plus h formula. Let's see what happened that caused that to occur. When I look at this one and I substitute, remember that s is approaching the value of a, which is the price of our scone, $3.25. I can use the formula, which was given to us as negative 20s squared plus 150s minus 10, and subtract from it the value at $3.25, my profit at that amount, which turned out to be $266.25. When I combine these and try to substitute $3.25 for the price, I get 0 over 0. When I combine them together, I still have 0 over 0, of course, since it's essentially the same. But I'm guessing that this means that s minus 325 must cancel. That means that it must divide it evenly. Unfortunately, this is a horrible problem to try to factor. So instead, I went to long division. Remember to take the numerator inside the division symbol and the divisor outside. And you estimate negative 20s squared divided by s is negative 20s. Then you multiply, and then you change the signs to subtract. And you bring down the next term. Again, estimate 85s divided by s is about 85. I add the 85, multiply it out for the next row, and subtract to bring down. Now I get that this is equal to exactly negative 20s plus 85. I replace this more complicated rational function with a simplified fraction, which represents the same value except at 325. The limit doesn't get to 325, so this is okay. Then when I evaluate the limit again, I get 20. The profit is changing in a positive direction at that price. I could choose to increase it more. If it were negative, I definitely would not, because the profit would drop when I increase the price. Let's now take a look at our last example, number 11. This is a shorter example where we look at the graphs of two vehicles traveling on a road side by side, and their position functions are shown here. Now the cars are just going down the road straight ahead. The graphs represent their position with respect to time. What can we say about their instantaneous and average velocities? Which vehicle has traveled farther at 2 seconds? At 2 seconds, the orange one is here and the blue one is here. At 2 seconds, the blue one has traveled further. Remember that this is position here on the y-axis, the vertical, and this is time here on the horizontal x-axis. So I've traveled further for the blue function, f of t. What is the approximate velocity of each vehicle at t equals 3 seconds? Well, the approximate velocity means I need to find the derivative to really know what it is, but I can't get the derivative. The best I can do is to estimate the slope of the tangent line at that point with the slope of the secant line. So if I'm going to take the velocity of each vehicle at 3 seconds, then I need to be considering the points over here. When I look at the one on the blue graph, it's a line. So the slope of that line would tell me what the instantaneous velocity was. The line has a slope of 1, moving up 1 and right 1. So the derivative at 3 on f must be f prime of 3 equal to 1. That's the instantaneous velocity. We could call this maybe 1 foot per second, since the distance is measured in feet and time in seconds. What about the second one? The second one is more difficult. To do the second one, we actually have to estimate a couple of points. This point right here, I'm going to estimate is about 3, 2. Now I need to find something else that looks like it would be on the tangent line. So I'm going to try to draw the graph, and it looks to me like the tangent line is coming down through the ordered pair to 0. So I compute g prime at 3 by taking the limit of the slope, the difference quotient. In this case, this is going to be as my value gets close to 3. And I can use the slope that I've estimated for my actual value. This is simply going to give me 2 minus 0 divided by 3 minus 2, which gives me 2 over 1, or 2 feet per second. That means that the one in orange is traveling faster than the one in blue, even though the one in blue is further along. Let's take another look at this and compare it in a different way. Did I really need to estimate that? The answer is no. If I were to look at the original f of t, the tangent line looks like this. If I were to take the graph g of t and draw the tangent line, do you see that the tangent line on g is steeper? A steeper line has a higher slope. So it must be moving faster, since the slope of the tangent line is the instantaneous velocity. It was not necessary to estimate. I can do it by the shape of the slopes of their tangent lines. Which vehicle is traveling faster at 4 seconds? Well, at 4 seconds, again, if I'm talking about the speed, I need to know what the instantaneous velocity is. On the blue graph, it still looks like this. On the orange graph, it looks like this. Both lines are positively sloped, but again, g of x is moving much faster. So that means that g is moving much faster on this one. So our answer for the second question was g of t. And the answer for C is also g of t. What about the last one? What is true about the positions of the vehicles at t equals 4 seconds? Well, if I'm looking at t equal 4 seconds, that's where they intersect. If they intersect there, it means they've reached the same position, which means that they're at the same point on the road. Although the blue car is moving faster, or the orange car is moving faster than the blue car. This is the end of this particular video. I hope that you will join me now and you will come for the next video in our study of derivatives.